Hello students, yet welcome to another session on electronic devices. And today we are going to discuss two major op amp applications, which are integrator and differentiator. As its name indicates, the integrator amplifier performs the mathematical procedure of integration that causes the output to change over time. Now, integrator using operational amplifier. There are several types of integrator that can be made using operational amplifier. Some of the most used type of integrators are ideal active op amp integrator. The second one is non-inverting integrator and practical integrator. Now let's discuss these types one by one. An ideal active op amp integrator. Now, if we replace the feedback resistor RF of the ideal amplifier in the inverting mode, we obtain an integrator. The input voltage Vin is applied to the negative input terminal through the resistor Ri. Now, in capacitor current, I that is equal to C dVc by dt. And if we apply KCL in the circuit, we get Vin minus Va by Ri is equal to ddt of Va minus V0. Now, as node B is grounded, node A is also at ground potential. Now, from the concept of virtual ground, we get Va is equal to 0. Therefore, Vin by Ri is equal to C dVc by dt. And cross multiplying this equation, we get minus Vin dt by Ric is equal to dV0. Now, taking both side integrations, we get the value of V0 as minus 1 by CRI integration of Vin t dt. The amplifier therefore provides an output signal which is proportional to the integral of the input voltage. Now, the non-inverting integrator. The circuit diagram of an op amp in the non-inverting integrator is displayed. In this mode of operation, the negative input terminal of an amplifier is grounded and the input voltage Vin is applied to the positive input terminal through the resistor R. In the non-inverting amplifier, the voltage between inverting and non-inverting terminal is same. So voltage Va in non-inverting terminal is equal to Va in the inverting terminal. Now hence, in this case, the output voltage V0 becomes V0 that is equal to 1 by CR integration of Vin t dt. Now the practical integrator. An ideal integrator has two limitations. These are, in the presence of input signal, also the two components, namely offset voltage and bias current, contribute an error voltage at the output. Thus, it is not possible to get a true integration of the input signal at the output. Output waveform may be distorted due to such an error voltage. Now, another limitation of an ideal integrator is bandwidth, which is very small. Hence, an ideal integrator can be used for a very small frequency range of the input only. These limitations of an ideal op amp can be minimized in the practical integrator circuit that uses a resistance Rf in parallel with the capacitor Cf. The practical integrator circuit is displayed. The resistance Rcomp is also used to overcome the errors due to the bias current. The resistance Rf reduces the low frequency gain of the op amp. Now let's discuss about the applications of integrator. These circuits are mostly used in the following applications: in analog computer for solving differential equations, in analog to digital converters, in signal and wave shaping circuits, and in ramp generator. And with this, we have come to an end of this session. And today we have learned introduction to integrator amplifier using op amp, types of integrator amplifiers, characteristics and circuit analysis of an ideal active op amp integrator, fundamentals of non-inverting integrator, and limitations of an ideal integrator, and with the implementation of practical integrator. We will meet again with another lecture of op amp applications. Until then, keep watching and keep learning. Bye.